Hi students, and welcome to this lecture on continuity of functions. In a day-to-day life, we see many examples of events or things that are continuous in nature. Be it a railway track, a free-flowing river, the sound waves emitted from the horns of vehicles that enter our ears. These are all examples of continuous things or events. But things become discontinuous as well at some points. So in this lecture, we will talk about the continuity of functions and also see why functions become discontinuous at some points. So let's start this lecture. So first of all, let me ask you something. What does continuity in general mean? Continuity means that the state of being uninterrupted or the state of being continuous without any joints or breaks. Now we are talking about calculus, and the entire calculus is based on the concept of functions. So in this lecture we are going to study about continuity of a function. Now let us say that this is the graph of y equal to f of x. Now a is any point on the x-axis and the corresponding value of y would be f of a. Now let's take a point very much close to a but on the left side of it, that is, it is less than a, but actually it's very much close to a. Let us say that this is a minus h. The corresponding value of y would be f of a minus h. Similarly, if we take a point on the right side of a that is very much close to a but is actually greater than a. Let's take it as a plus h, where h tends to 0. Now the corresponding value of y would be f of a plus h. Now continuity of a function is defined as if the limit of fx when x tends to a negative, that is the left hand limit of fx at the point x equal to a, is equal to limit of fx when x tends to a positive, that is the right hand limit of fx at x equal to a is equal to f of a, that is the value of y at the point x equal to a. Then if this condition holds, fx is said to be a continuous function at x equal to a. Now let's come again to the meaning of continuity of functions in mathematics. If we say that a function is continuous at a point a comma f of a, then it means that there are no holes or gaps or that it is unbroken at the point a comma f of a. So the same concept of continuity applies in mathematics, and the literal meaning is that if a function does not have any holes or gaps at any point a comma f of a, then the function is said to be continuous at the point x equal to a. Now if a function is not continuous at any point x equal to a, then it is said to be discontinuous at the point x equal to a. So the condition for any function to be continuous at a point x equal to a is that the left hand limit should be equal to the right hand limit, and which is equal to f of a. Once again, for a function to be continuous at any point x equal to a, the left hand limit is equal to the right hand limit is equal to f of a. Now let's take different cases when fx is discontinuous. Now case number 1 is if limit of fx when x tends to a negative is not equal to the limit of fx when x tends to a positive, that is the left hand limit is not equal to the right hand limit. And we know that when the left hand limit is not equal to the right hand limit, then the limit does not exist. So if we say that the limit does not exist at point x equal to a, then the function is surely discontinuous. The second case is if the left hand limit is equal to right hand limit but is not equal to f of a, that is the limit exists, both left hand and the right hand limit are equal, but these are not equal to the value of function at the point x equal to a. So in such case we say that the limit exists but is not equal to f of a. Now let's come to the case number 3, that is f of a is not defined. In such case as well, fx is a discontinuous function. Case number 4 is if one of the limit does not exist. So the different cases are if the left hand limit is not equal to right hand limit, then the function is discontinuous. If the left hand limit is equal to right hand limit but is not equal to f of a. The third is f of a is not defined, and if one of the limit does not exist. Now let's see these cases one by one. Case number 1 is left hand limit is not equal to the right hand limit. Now let's try to visualize it. This is the graph of y equal to fx. Now we see that the left hand limit is equal to L2 and the right hand limit is equal to L1. That is, if we approach the point A from the right hand side, then the value of the function is L1, and if we approach the point x from the left hand side, the value of the function becomes L2, and we see that L2 is not equal to L1. So in such case, we say that the limit does not exist, and so the function is discontinuous. So let's try to see an example. Discuss the continuity of fx equal to the greatest integer function of x plus 2 as x approaches 2. Now the given function is fx equal to the greatest integer function of x plus 2. Now if x is just less than 2, or we try to see the left hand limit, then when x is just less than 2, the value of greatest integer function of x would be equal to 1, and so fx is equal to 3. So when x lies between 1 and 2, then the value of fx would be 3, and when x is slightly greater than 2, then the value of greatest integer function of x would be equal to 2, and hence fx is equal to 4. So for the values of x which lie between 2 and 3, the value of fx would be equal to 4. Therefore we see that the left hand limit is equal to 3 and the right hand limit is equal to 4. Therefore the left hand limit is not equal to the right hand limit, and so the limit does not exist, and hence we can say that fx is discontinuous at the point x equal to 2. Now let's see case number 2, that is the left hand limit is equal to the right hand limit but is not equal to f of a. Now let's try to visualize it. This is the graph of y equal to fx. Now we see that if we approach x from the left side of a, then the value of fx approaches to L, and similarly if we approach a from the right hand side, then again the value approaches to L. Therefore the left hand limit is equal to the right hand limit and is equal to L, but the value of function at the point x equal to a is f of a, and which is less than L, or which could be greater than L but is not equal to L in such case. Therefore we say that the left hand limit is equal to the right hand limit but is not equal to f of a. Therefore the function is discontinuous at the point x equal to a. Now let's try to again see an example to understand this. Discuss the continuity of fx equal to x square plus 1 when x is greater than 2, 1 when x is equal to 2, and x plus 3 when x is less than 2. Now let's first try to calculate the left hand limit. So the function is x plus 3 when x is less than 2. Now let us say that x is equal to 2 minus h and h tends to 0. So we put the value of x here in this expression and get the limit as equal to 5. Similarly, when we try to calculate the right hand limit, we put x equal to 2 plus h where h tends to 0. H is a positive quantity. So we see that the value of fx when x is greater than 2 is x square plus 1. So we put the value of x equal to plus h and get 2 plus h whole square plus 1, h tending to 0, and therefore the limit is equal to 5. Now we see that the left hand limit is equal to the right hand limit, but also given that fx is equal to 1 when x is equal to 2. So f of 2 is equal to 1, which is not equal to the left hand limit and the right hand limit. Therefore we can say that fx is discontinuous at the point x equal to 2. This is the value of function fx equal to x square plus 1 when x is greater than 2 is equal to x plus 3 when x is less than 2 and is equal to 1 when x is equal to 2. Now we clearly see that the right hand limit is equal to the left hand limit, but suddenly see that the value of f of 2 is equal to 1. Left hand limit is equal to the right hand limit but is not equal to f of a. Therefore fx is a discontinuous function at the point x equal to 2. Now let's look at case number 3. If f of a is undefined. So this is the graph of y equal to f of x. When x approaches a from the left hand side, then the value of function is equal to L. Similarly, when x approaches a from the right hand side, then again the value approaches to L, but the function is not defined at the point x equal to a. Therefore there is a break at this point x equal to a. Therefore we can say that the function is discontinuous. So once again we try to see an example. Discuss the continuity of fx equal to x square minus 4 divided by x minus 2 at x tending to 2. So we have to discuss the continuity of fx at the point x equal to 2. Now we clearly see that it is not defined at the point x equal to 2. So if we put the value of x equal to 2, this function fx becomes undefined. Now fx is equal to x minus 2 into x plus 2 divided by x minus 2. Now if I say that x is not equal to 2 but is close to 2, then we can cancel this factor x minus 2 and x minus 2 and we get fx equal to x plus 2. Now limit of fx when x tends to 2 is equal to 4. Therefore the left hand limit and the right hand limit is equal to 4. But we see that f of 2 is not defined. Therefore fx is a discontinuous function at x equal to 2. So this is the graph of x square minus 4 divided by x minus 2. In this case we see that the left hand limit is equal to 4 and the right hand limit is also equal to 4. But the function is not defined at the point x equal to 2. Thus fx is discontinuous at the point x equal to 2. So let's try to solve a few IT problems. Now this problem appeared in 1983 and it is the function fx equal to log of 1 plus ax minus log of 1 minus bx whole divided by x is not defined at the point x equal to 0. Now the value which should be assigned to f at the point x equal to 0 so that it is a continuous function at x equal to 0 is option number A is a minus b, option number B is a plus b, option number C is log of a plus log of b, and option number D is none of these. So in this problem we have been given a function fx and it is not defined at the point x equal to 0. We have to assign a value to f at the point x equal to 0 such that the function becomes continuous at the point x equal to 0, and we have been given the 4 options. So let's try to solve it. Fx is equal to log of 1 plus ax minus log of 1 minus bx whole divided by x. Now for f to be continuous at the point x equal to 0, limit of fx when x tends to 0 should be equal to f of 0. Now this is from the basic definition of a continuous function. Now first of all let's try to find out the limit of fx when x tends to 0, and fx is log of 1 plus ax minus log of 1 minus bx whole divided by x. Now what we do is we multiply this with a and divide it by a, and similarly we divide and multiply this part with b so that fx becomes a times log of 1 plus ax divided by ax plus b times log of 1 minus bx divided by minus of bx. Now we have transformed fx to this form. Now we also know that log of 1 plus x divided by x when x tends to 0 is equal to 1. Therefore log of 1 plus ax divided by ax would also be equal to 1 when x tends to 0. Thus the limit of fx when x tends to 0 is equal to a plus b. Now fx has to be continuous at the point x equal to 0. So f of 0 must be equal to the limit of fx when x tends to 0, and which is equal to a plus b. Therefore f of 0 is equal to a plus b, and hence we can say that option number B is correct. Now let's see one more example. This problem appeared in IITJ in 1990 and it is that fx is equal to 1 minus cos of 4x divided by x square when x is less than 0 is equal to a when x is equal to 0 and is equal to under root of x divided by under root of 16 plus root x minus 4 when x is greater than 0. Now determine the value of a if possible so that the function is continuous at the point x equal to 0. Now we have been given a function fx and these are the expressions of fx when x is less than 0, x is equal to 0 and x is greater than 0. Now we have to determine the value of a such that fx becomes continuous at the point x equal to 0. So let's first of all try to calculate the left hand limit. Now the expression given to us when x is less than 0 is 1 minus cos of 4x divided by x square. So let us say that x is equal to 0 minus h. Therefore we put the value of x in the expression and get limit of 1 minus cos 4 times 0 minus h divided by 0 minus h whole square. Now h tends to 0. Now this is equal to limit of 1 minus cos 4h divided by h square when h tends to 0. Now 1 minus cos 4h could be written as 2 sin square 2h and the denominator is h square. Now what we do is we multiply and divide it by 4. Therefore, we get the expression as 8 into sine squared 2h divided by 4h square. Now, the value of this is equal to 1 because sine x by x when x tends to 0 is equal to 1. Now, this limit is equal to 8. Therefore, we can say that the left hand limit of fx is equal to 8. Now, similarly, we'll try to calculate the right hand limit. Is equal to limit h tends to 0 under root of h divided by under root of 16 plus under root of h minus 4. Now, what we are going to do is we are going to rationalize it. And so, we multiply and divide this expression by under root of 16 plus root h plus 4. Now, this becomes under root of h into under root of 16 plus root h plus 4 divided by root h. Now, root h and root h gets cancelled, and when we put h equal to 0 in this expression, we get the value as equal to 8. Therefore, we see that the right hand limit is equal to 8 and the left hand limit is also equal to 8. Therefore, LHL is equal to RHL, and hence limit exists at the point x equal to 0. Now, for function fx to be continuous, we see that f of 0 must be equal to the left hand limit, and which is equal to the right hand limit. Therefore, f of 0 is equal to 8. Now, f of 0 is nothing but equal to a, and so we can say that a is equal to 8. So, let's try to solve one more example. Let fx is equal to 1 plus modulus of sin x whole to the power of a by modulus of sin x when x lies between minus pi by 6 and 0, is equal to b when x is equal to 0, and is equal to e to the power of tan 2x divided by tan 3x when x lies between 0 and pi by 6. Find the value of a and b so that fx is continuous function at x equal to 0. So in this problem, we have been given fx and we have to find the values of a and b so that fx is a continuous function at the point x equal to 0. So, given that fx is equal to 1 plus modulus of sin x whole to the power of a by modulus of sin x when x lies between minus pi by 6 and 0, is equal to b when x is equal to 0, and is equal to e to the power of tan 2x by tan 3x when x lies between 0 and pi by 6. Now we have to find the values of a and b so that fx is a continuous function. Now, for a continuous function, limit of fx when x tends to 0 is equal to f of 0. Now, let's first try to calculate the right hand limit, because the expression for calculating the right hand limit does not have any a or b. So, the right hand limit is equal to limit of e to the power of tan 2h by tan 3h when h tends to 0, because we substitute x equal to 0 plus h and get the value as tan 2h by tan 3h. Now, what we do is we multiply and divide the numerator by 2h, and similarly we multiply and divide the denominator by 3h, so that we get the expression as tan 2h by 2h into 2h divided by tan 3h by 3h into 3h. Now, tan of 2h by 2h when h tends to 0 is equal to 1, and similarly tan 3h by 3h when h tends to 0 is equal to 1. So, we get 2h by 3h and h gets cancelled, so the value of limit is equal to e to the power of 2 by 3. Therefore, we can say that right hand limit is equal to e to the power of 2 by 3. Now, as fx is continuous, so RHL should be equal to LHL. Now, LHL is equal to limit of 1 plus modulus of sine minus h whole to the power of a by modulus of sine of minus h tending to 0. Now, this gets reduced to limit of 1 plus sine h to the power of a by sine h when h tends to 0. Now, we see that when h tends to 0, this reduces to the form of 1 to the power of infinity. And we know that 1 plus fx to the power of 1 by gx when fx tends to 0 and gx tends to 0 could be written as equal to e to the power of limit fx by gx x tending to 0. Now, we write it as e to the power of limit a sin h by sin h tending to 0. Sin h and sin h gets cancelled, and we get as equal to e to the power of a. Now, we know that RHL is equal to e to the power of 2 by 3 and LHL is equal to e to the power a. And also, for fx to be continuous, f of 0 should be equal to the left hand limit and the right hand limit, and f of 0 is equal to b. Therefore, from this we get a equal to 2 by 3 and b equal to e to the power of 2 by 3. Now, let's try to see how to check the continuity of a function at the extreme points of interval. Let us say that a function fx is defined in the interval a, b. Now this is a closed interval. That is, points A and B are included in this interval. Now fx is continuous at left end, that is x equal to a, if limit of fx when x tends to a positive is equal to f of a. That is, the right hand limit of fx at the point x equal to a is equal to the value of the function fx at the point x equal to a, which is equal to f of a. Here we don't need to calculate the left hand limit. So if the right hand limit at the point x equal to a is equal to the value of the function at that point, or f of a, then fx is continuous at the left end, that is x equal to a. And fx is continuous at the right end, that is x equal to b, if limit of fx when x tends to be negative is equal to f of b. Or in other words, we can say that the left hand limit of fx at the point x equal to b is equal to f of b. Then in such case, we say that fx is continuous at the right end. Here we don't need to find out the right hand limit at the point x equal to b. So for checking the continuity of a function at the extreme points, what we do is, for the point a, we check the right hand limit, and if it is equal to f of a, then it is continuous at the left end. And for the right end, we check the left hand limit, and if it is equal to the value of f of b, then we say that fx is continuous at the right end, which is x equal to b.